So based on the step index optical fiber, that is based on the refractive index profile, we classify them accordingly as step index and graded index optical fiber. So first one, let us talk about the step index optical fiber. In this case, from the name itself you can understand that the variation in the refractive index is happening in form of steps. So for that one we say that, for example, this again the classification is according to the mode they support, that is the single mode or the mono mode which we said earlier, and the multi modes. The step index will also be classified on those the modes and which these fibers are supporting, but mostly the multi-mode fibers are in operation. So based on that, let us discuss more about this step index optical fiber. So here in a step index optical fiber, the refractive index of the core is greater than the refractive index of the clouding, and there is uniformity maintained from input end to the output end. So throughout there is an uniform refractive index which is almost greater than the refractive index of the clouding from the input end to the output end. So we say that in step index optical fiber, the refractive index of the core, we can refer this in terms of let N1 is uniform throughout the fiber, which is slightly greater than the refractive index of the clouding, which is written as N2. So the condition is that N1 is slightly greater than N2. So that we have to maintain throughout the step index optical fiber. And in this case, we give the basic thing in terms of the diagram as, so this is your optical fiber. Okay, this is the refractive index, this is at the input section, this is at the output. Here we call this as the diameter of the step index optical fiber. And here, as we are talking about the single mode step index optical fiber. So how to vary this step index optical fiber based on the modes they support? For that one we say that 2A is supposed to be approximately equal to 2 to 8 micrometer in size. Now like that, if we take the case with respect to this one, that is the multi-mode, we draw it as like this. Now you can see the variation there. This is the refractive index profile of a step index multi-mode fiber. This is at the input section, at the output. So this is your core diameter. This is obviously about approximately equal to 50 micrometer. This is for the second case of an optical fiber which is happening in steps, which is a multi-mode step index optical fiber. So these fiber dimensions are even restricted to your single mode and multi-mode optical fibers respectively. So both these conditions can be stated in terms of the step index or either any kind of a material which is coming under the single mode and the multi-mode. The fiber dimensions here are maintained as 2A is approximately equal to 2 to 8 micrometer in size, and for a multi-mode it is 2A is approximately equal to 50 micrometer in size. So this is even applicable for all the other types of single and mono mode optical fibers, that is for step index as well as for the graded index optical fiber. But here the variation is with reference to the refractive index, which is almost maintaining uniformity throughout the diameter of the material, that is the fiber. So this is how we can give diagrammatically the step index optical fiber. Now let us see the transmission of a signal in a step index optical fiber. Transmission of signal in a step index optical fiber. Now for this one we say that let us consider a step index optical fiber in which we consider the light ray passing through that core of that optical fiber, and here we are considering the light ray based on a figure. Let me show it in that. So this is the core. Let us take this as the input end and this is the output end. First of all, this is the input signal which we are giving. So this is the input signal at one of the ends of the fiber material. The amount of a light ray is propagated along this direction, and this, let us name this direction as 1, and there is light ray moving in this direction as well. One more light ray moving along this direction in this path. Let us name this direction as 2. The path traveled is the second one. Now in this case, so let us refer to the idea over here. Consider a light signal passing through the core of an optical fiber. Now we are talking about the light signal. Here in case of an optical fiber, the light signals, we generally don't call it as a light signal, but indeed we call it as a pulse. That is, we can call it as a signal pulse. So this signal pulse is usually represented or given in terms of a digital form. Digital form in the sense we give it in binary numbers such as 0 and 1, and you know that basically the on and off conditions are represented in terms of 0 and 1. If 0 is supposed to be off condition and 1 is on condition as far as your circuits are concerned. But here we call it as a pulse. Pulse signal is what we are calling, 0 and 1 respectively. So here we say that the signal is sent, is called as a pulsed signal. This signal is represented in zeros and ones, almost binary, zeros and ones. Consider one such pulsed signal. Consider one such pulsed signal propagating through an optical fiber as shown in the figure. The first signal pulse travels along the principal section or axis of an optical fiber. So this is what we call it as the principal section or the fiber axis, right? Now when it travels along the axis of an optical fiber, we say that first it travels along the principal section or axis of an optical fiber, or the direction section selected is a shorter route. This is a shorter route. Simply there are no disruptions in the signal. Directly it moves on and hits the output end here. Okay, output end. Now it travels along the shorter route and reaches the output end fastly, and therefore reaches the output end faster. Now we say about the second signal. It is traveling in the form of steps, or otherwise we can call it as a zigzag way. So it reaches after a certain amount of a time delay. So here the second signal, the signal 2 takes a longer route in a zigzag path, and reaches the output end after some time delay. So when it reaches the opposite end after a certain amount of a time delay, there is a disruption in the quality of the signal. and this disruption in the quality of the signal is called as the intermodal dispersion. So because of which there is disruption in the signal. So both the signals are not meeting at the same time. Both the signals are not meeting at the same time. Now this disruption is called as intermodal dispersion. So what will happen means the signal at the output end is supposed to be a broadened one. Broadened in the sense, so the signal which we have sent over here, you can see the diagram here. So in this diagram we see, so this is the input signal and this is how you get the output signal. So there is variation in the signal over here. This is a broadened signal which we are seeing here. So because of this dispersion, the signal at the output end is broadened. So as the signal is broadened, so it reduces, that is, this dispersion reduces. So the transmission rate and capacity of the optical fiber is supposed to be reduced because of this intermodal dispersion. So there is certain variation there. So uniformly it is maintained. So the first signal is supposed to be traveling along the same path and reaching the output end as fast as it could. But whereas the second signal, which is taking a different route, means it is following a different path, it is following a different mode, and therefore it is reaching after a certain amount of a time delay. So there is a mismatching of the signal over here, which we can say that it is referred to as an intermodal dispersion. So what we have done in case of the light ray, which was constructive and destructive interference, so the same kind of a phenomenon is happening even in case of the step index optical fiber, leading to form an intermodal dispersion, so which reduces the transmission rate and capacity of an optical fiber. So this was what was happening in case of a step index multimode fiber, because as we are selecting more than one route here for the propagation of a light ray, we are calling it as a step index multimode fiber. So this is the thing which is happening, which is leading to intermodal dispersion. Now to rectify this intermodal dispersion, another kind of a optical fiber was used, that was called as the we call it as the graded index optical fiber. So let us see the case regarding graded index optical fiber. The second one, now graded index optical fiber. So this is the second type of an optical fiber to reduce the intermodal dispersion. So in this case of a graded index optical fiber, the refractive index of the core is supposed to be maximum at its center, and this refractive index, which is high, will be decreased because of the increment of the radius of the core keeps on changing. Then this particular kind of the refractive index of the core also changes with the radius or the diameter of the core material. So we say that in a graded index optical fiber, the refractive index of the core is maximum at the center of the optical fiber, which gradually falls due to increase of the radius of the core. Now the variation of the refractive index, the variation of the refractive index of the core with the radius is given by n of x is equal to n1 into 1 minus 2 delta into x by a whole power p whole square. This is the variation what we are giving for the variation of the refractive index of the core with the radius of the core, which is given by n of x is equal to n1 into 1 minus 2 delta into x by a whole power p whole square, where n1 is the refractive index at the center of the core. Okay, delta is the fractional difference in the refractive index of the material. Refractive index of the material given by delta equal to n1 minus n2 by n1. So this is how we give. And here in the second case we have a as the radius of the core and p is called as refractive index profile number. So this is how we give it as n of x is equal to n1 into 1 minus 2 delta into x by a whole power p square. So this is how we can calculate the variation of the refractive index of the core with the radius of the core as given by this basic equation. Next, so this is about a graded index optical fiber. Now in case of this, how the transmission of a signal is happening because of the variations in the refractive index, how does it affect the pulsed signal which is moving from the input end to the output end of an optical fiber? Let us see it now. Here we say that change in the refractive index of the given material is changing radially. Radially in the sense, here we can draw the figure like this. This is for the graded index optical fiber corresponding to the step index 1. Okay, this was in case of your step index optical fiber. This was at the input end. That is for the step index 1. This is your refractive index profile, and here this is the change what we notice in a graded index optical fiber. Check it out here. This is how it radially happens. Okay, now we can say that this is for N1, this is for N2. Okay, so this is happening radially. So this is your diameter of that respective core. You can write it as A, this is for step index, and D is for graded index optical fiber. So it is varying radially. Step index, how does it work? It is radially happening in case of a graded index optical fiber. The variation of the core with respect to the changes in the refractive index lead in that way. So let us explain the transmission of signal in a graded index optical fiber now. So we come to the transmission of signal in graded index optical fiber. Transmission of signal in graded index optical fiber. So in this case we consider the following example. So this is your optical fiber. So we want a light ray to propagate along one direction, right? Now this is the variation of the signal here, how it is happening. Let us see. Okay, so this is light ray 1 and this is light ray 2. This is a signal which we are giving at the input end. This is the input signal. Now let us study this particular factor. In the first case, the light ray 1, it is traveling along the same kind of a route, that is a shorter route, whereas the second ray is taking a longer route. In step index it was happening in a zigzag manner, but here it is radially moving and it is forming a kind of a curved path. But even though both of them reach at the same time. So what makes those particular rays, even though they are selecting two different paths or two different routes, one is even though the shorter one and the other one is also a longer one obviously, but what makes those two signals travel at the and reach the output end at the same time? So when they meet at the same time, the intermodal dispersion is supposed to be changed. Means the defect which was occurring in case of a step index optical fiber is rectified using your graded index optical fiber. So what are the parameters which are making that particular routes selected by the different signals to stay tuned and form and an undiffracted or any kind of a dispersion, that is the intermodal dispersion is rectified. Let us see that particular factor. So in case of the first one, we can say that as shown in the figure, consider a signal pulse traveling through graded index optical fiber in two different paths, 1 and 2. The light ray, the light signal 1 travels along a shorter route, reaches the output end as it travels along a principal axis inside the core, having greater refractive index, whereas the signal 2, though travels along a longer route, reaches output end at the same time as signal 1 with a lesser refractive index. So both are supposed to be, what we can say that there is compatibility in case of the either if the route is supposed to be very much shorter but the refractive index is supposed to be greater. Regarding the second one, though it is traveling at a longer route but it is traveling in a lesser amount of a refractive index. So both are supposed to be compensated with respect to one another. Because of this particular amount of a compensated nature of both the light signals, they are reaching at the output end at the same time. As they are reaching at the same time, the process or the disrupted signal which we have considered it as intermodal dispersion is supposed to be completely rectified in case of a graded index optical fiber. So the intermodal dispersion in step index optical fiber happened is completely rectified in graded index optical fiber. So these are the changes what we see in case of this. So here the signal is not supposed to be broadened, but with some highest amount of clarity is what we can get it in the output signal here. So these are the changes what happens in case of a step index 1 and the graded index optical fiber because of the variation in the refractive index of the material. So here we can close regarding the transmission of a signal in a graded index optical fiber.